So whatever you're saying will be recorded. It is my great pleasure to introduce our today's speaker, Professor Erwin Bolthausen from University of Zurich, Switzerland. I should say that I first encountered the name of Professor Bolthausen when I was still a student. In the last years of university, we read his papers in our probability seminar. And Professor Bolthausen is one of the most prominent probabilists of the last, or maybe 30, 40 years, maybe 50 now by now. He's been active for 50 years in probability, starting with the classical areas, including central limit theorem. And actually, one of his earlier papers is devoted to the central limit theorem for empirical processes indexed by convex sets on the plane. And I started my PhD with a very similar topic, but then I changed because it was quite difficult. Anyway, and then he continued and was doing less traditional things. And today's talk is also on a topic which is not exactly in the mainstream classical probability, but still very interesting. So, Erwin, please start your talk.
Okay, thank you very much for the for this very kind introduction. Okay, the talk is a little bit of a, okay, it's a survey talk. And actually it covers topics on which actually I'm not really an expert. But it's connected with a paper I had written a couple of years ago with a motivation about which I will talk just at the end, because okay, we took it up recently, and we have some recent work in progress about which I can talk if there is enough time at the end. The starting point is I have to introduce what is factor graphs are and measures on factor graphs. Well, the starting point is, okay, everything is finite. I have a finite set, so that's the alphabet, and then I have a finite set of what is called variable nodes here, and then one is looking at probability distributions on this product space, of course, which is a finite set, and there are just of the form where you are just having a couple of functions. So the functions are indexed by always indices which I take A. And this, okay, I will shortly give a graphical picture. These A are called the function nodes. Yes. And then to every A there is attached a subset of the variable nodes. And the function is mapping, okay, this restricted product space to the positive real line. And then what one is doing when one is plugging in, okay, you're taking an element X from this space. Here you restrict it to this okay, what I would call boundary of the function node. And apply the psi A, and then I'm taking all the product. And then if I want to have a probability measure, of course, I normalize it here. Okay, I'm taking F, capital F, as a set of function nodes here. So that's okay. Often the components of a vector X here, so of an element capital X. So I'm using capital X for elements here in that. So if you just have functions on individual xi's here, then I'm just writing them as ci of xi here, so which is okay. You see on the next picture here, so how it looks like. And then one is writing down that's actually convenient for visualization, that you have a graph structure. You're just taking a bipartite graphs where you have connection between the function nodes and the variable nodes here. If I is in the boundary of A here, so then you can also define the boundary of I. So I'm using always I or J as for the variable nodes. And I'm taking the function nodes which to which I belongs as in the boundary. So okay, I have a picture on the next slide here. So as a rule, I'm just taking, okay, squares for the function nodes and circles for the variable nodes. And you see, I'm having here a bipartite thing. So for instance, if you take this function node, it means that the corresponding function acts here on these 3 variables here. And here you have just one function node which is just as attached to one variable. So you're just, okay, having just one function acting on this variable here. And then you're taking the product of everything and normalize it. So that's a measure here. So that's just a convenient graphical representation here. Now, of course, okay, standard examples for that are okay, Markov chains. Okay, everything for the moment is finite. So you just take Markov chains on a discrete finite time slot. That's of course falling into this category. But where of course in that case the function nodes all have degree 1 or 2. So in that case here, easy model is also okay. I don't write it down. I guess everybody knows what the easy model is. I will not talk about it. So there you have a finite okay. For instance, a square lattice here. And then if you want to do it in a factor graph, of course, the square lattice corresponds to these variable nodes. And then because you just have pair interactions, you are just having one function nodes between neighboring variable nodes on the graphs here. So now, what is also happening often, and actually many things I'm talking here today about are related to the fact that often this function itself are random functions. So they are not just fixed functions, but they itself are defined as random elements, say, on a probability space here. So now, as a rule for this probability space, I'm always taking this P, okay, blackboard called P. So which is governing the law of this psi A as random variables here. Now, okay, one of the basic models is, okay, if you want the simplest model, but actually that turned out to be very complicated, is this Shelton Kirkpatrick model from statistical physics. Okay, I will later talk more about it. So it has okay an alphabet here, which is just minus 1 plus. In physics jargon, these are spin variables, okay, but it's just minus 1, 1. And the variable nodes are just, say, 1 up to n. And you should always think, okay, n is always finite, but one is always interested in the behavior for large n here. So. And then in that case, you see okay, I just write down what the measure is. So I'm taking element x, which is in minus 1, 1 to the power n, with components xi, and then, okay, there is a prefactor and the parameter beta, in physics jargon, the inverse temperature. Okay, I divide by square root of n. It turns out actually that this is the right choice. And then I'm having interactions between xi and xj for every pair I and j. And this is given by some coefficients. If they would just be fixed coefficients, of course, it would perfectly fit in our picture here. But it's now assumed to be random variables here. Okay, then you can think I'm fixing the omega, and then there are fixed numbers here. So I'm having that. And then I'm also allowing that every single xi can get a tilt by a parameter h. It's actually important for us because otherwise there is some symmetry which I don't like to have here. And then I normalize it, and I'm getting a probability distribution. But this probability distribution depends on this small omega. So of course it's a random probability distribution here. Okay, the JIJs are assumed to be standard Gaussian here. So the function nodes in this case are of course just can consider to be the pairs I and j, and in that case, of course, trivially, so the boundary of A is just A and j. So of course, just and then I have the psi given by that, and these functions acting just on one variable given by e to power hxi. Is that clear? Any questions? Or, no, a totally different dimension because it was actually obviously one of the first occurrences of this algorithms I'm talking about is in communication, so linear block codes for noisy channels. Yeah, so okay, formally it's easy to describe. You have a set of code words, and the code words in that case, okay, our alphabet is 0, 1. So, but I'm taking 0, 1 as a field of two elements. Yeah, so because you're arguing with linear algebra here. So the set of code words is just the linear subspace of this n-dimensional vector space here. And okay, it's always assumed that the dimension is smaller than n, so this linear subspace. And that of course can be described by standard linear algebra. So by the set of code words is just elements in this vector space, okay, which is just 0, 1 to the power n, which satisfies this linear homogeneous linear equation x equal to 0. So this is an m cross n. What is called parity check matrix. Of course, it can have more lines, more rows than n. But okay, you can assume, of course, that it has maximal rank. Then it's an m cross n matrix here. Now, what the situation is that this code word is sent through a memory, so-called memory. Okay, it doesn't have to be memoryless. So the meaning is that you are just sending it at one place, and it can be distorted in the channel. So you get some noise on the channel here. So what you receive is maybe not what you have sent here. So. Now, in the case of a memoryless channel, you just have a probability distribution that you receive y, given that you have sent x. So in this case, where you just have the alphabet 0, 1, so you just have to specify with which probability you receive 0 if you have sent 1, or with which probability you receive 1 if you have sent 0 here. So that's given by this Q. So memoryless refers to the fact that what you receive in the end is a sequence of length n, and the probability given that you have sent x is given by this product measure here. So now, what you also can assume, and what is typically assumed, that the code words which are sent are coming with a certain probability distribution. And then okay. Pi. So for simplicity, one often assumes that you just have a uniform distribution over all possible code words. But that's in practice, of course, not very realistic. But okay, for theoretical computation, that's often assumed here. And then the probability that you receive y is just given, of course, you multiply that with these transition probabilities here. So you're getting a certain distribution on the messages you receive here. So. Now, what is the decoding problem? Of course, naturally, the decoding problem is you receive y, you want to know what x is sent here. Of course, if it doesn't make an error, then you're just taking x. Okay, your estimate is just y, but because you are having a noise in the channel, what one is doing is okay. There are several possibilities, but a standard thing is, of course, just doing the maximum likelihood estimate here. And then what you're doing, you're choosing the x, assuming here that the code words are sent with equal probability. The maximum likelihood estimate is just you are maximized, say this mu x, okay, given y, so which is just okay, given by this kernel here. So you're looking just with which probability y is obtained given x. And then you're just having this indicator function, namely that you have a code word. So because of course you want to get in the end, your estimate should be a code word. So you're just looking which you're maximizing over the x, which are satisfying this side condition that all of these parity checks are equal to 0, so lead to 0. So that you're in the code word. So you see that okay, if you fix y for the moment, that's exactly the structure we had before here. So with these functions psi given in this case in this special form here. So now you see, but because you are assuming, of course, that that y is in the end random. So in theoretical, if you want to derive properties, then you should assume that the y's, the received messages are coming with this distribution, and then you are in the same situation in principle like in the Shelton-Kirkpatrick model, where this probability distribution is random. So you have a random probability distribution because the y's are random here. So you are in principle you are in a similar situation like in the Shelton-Kirkpatrick model here. So now, no, you see, of course, in that case, you're just that you're not. It's more complicated than having pair interactions. So you can take as the function nodes the index for the lines, for the rows of the parity check matrix, and then the degree is you see that the degree of a function node is just the i's which have a coefficient in this matrix in this row equal to 1. So that's you have because here you're just summing essentially the xi's over the h which are 1. So in this situation here, so you're having this. You can it's perfectly fitting in our factor graph model here. So. Now, a particularly case is and that actually that I guess was the case where these belief propagations first came up. So it was at least one of the first cases where this LDPC code, LDPC is for low density parity check codes, which are now very popular. So in communication business. So their one typically has an H matrix which is pretty large. So of course it still has to be practical for implementation, but okay, the H matrix is pretty large, but it has okay the number of ones in this matrix are somehow sparse. So what you are doing is that you are taking every row the same number of ones, and in every column the same number of ones. So for instance, if you have a 3-4 low density parity check codes, then you have in every column you have 3 ones, and in every row you have 4 ones. But you can have more complicated schemes. But the key idea of this LDPC codes is that you have H large, and the number of ones are somehow okay, distributed like that, so that you have this situation here. So that is this is of course a special case of the situation we had before here. So now, okay, these are just okay examples where you are encounter these factor graphs. So now I'm coming now to this message passage passing here. So now what you are trying to do is kind of mimicking a Markovian structure here. So now what you are looking at are two sets of distributions. At the moment, if you have not seen it before, it looks a little bit strange here. So you have two sets of distributions, and the distributions are always just on the alphabet, not on any product space here. So and they are indexed by edges I and A. So the edges are okay, one variable node and one function node, because we have a bipartite graph. You just only have connections between function nodes and variable nodes here. And then you are having one family which I write with a hat, which goes from function nodes to variable nodes, and another one which goes from variable nodes to function nodes. But they are always, both of them are functions on the ith components. Here it's just of an element in the product space. So they are just functions on x. So I'm writing it them as functions of xi's here. So Now, they should satisfy certain equations. Now, I'm just writing here, this is approximate equations, but because typically it's convenient to define these equations only up to normalization here, so in the xi's here. So I don't care about normalization factors here. So now maybe it's the one here is simpler here. So what should be satisfied is that the nu from I to A as a function of xi should be up to normalization. You are taking the product over all boundaries elements. I'm having, okay, you see it on the next slide here within the graphical representation. You're taking all the function nodes at the boundary of I with the exception of A, and take that as a function of I and just multiply it here. So now how you are getting that from these ones is more complicated here. Again, that should be a function of xi. Now what you are doing is, again, you're doing essentially the same as here. So you are looking at the variable nodes now at the boundary of A, accepting I, and take that as x at xi, and then you are multiplying it with this basic function of this model here, which is restricted to the boundary of A, and then you are summing over the boundary elements of the function nodes A, where you fix the xi here. So okay, if you see it as a formula, it's a bit complicated, but if you see it on a graphical thing, then it's probably okay. It's not overly complicated. Maybe I just take this one first here. So this new IA is a function on the variable at xi, and that you are just getting by looking at the rest of the boundary of I, which consists in this case on 4 function nodes, but you are just taking the ones accepting A and multiplying them here. So that's just this here. So you have that. Now here, if you are looking at the ones from A to I, you are looking at the boundary of A, and you are looking at all the variable nodes. Okay, in this case there are 4. There are 3 besides I. What you are doing is you first take the function psi, which is a function of xi and xj1, xj2, xj3. Then you're multiplying that with these messages coming in from the chase, not from the i's, just from the chase into A. And then, okay, these are functions on xj. And then you are summing over xj1, xj2, xj3, so. And then you are getting a function which is a function of xi. And so, okay, this is just this formula here, so what they're doing. Now, of course, if you first see it, it looks a bit okay. You know what that's good for. So okay, the main aim is that it should help to compute approximate marginal distributions in the model here. So not just at one place. So you can. It's not difficult also to do it in 3-4 places if you like it here. So. But of course, there are natural questions. So for instance, have these equations solutions? So for instance, if you are having a finite factor graph, and the answer is typically yes. So they have typical solutions. So that's you actually can prove it. Okay, maybe I don't go into that. So how to prove that? So now, if they have solution, is there just one solution? So now you should think of that in principle, in the end, one wants to have things which are where the size of the system is becoming very large here. So and then the question is that often no. So there are situations where you have in principle one solution. I will give a trivial example where you have just one solution. But the most interesting cases are cases where it is not so clear if you just have one solution or many solutions. And that's an extremely important and extremely difficult point to decide if you have just one solution or if you have more than one solution. If you have more than one solution, how many you have. So Now the next question is, of course, what is that all good about? And then okay, one just can't give the answer. That the answer is very simple. If you are just looking at factor graphs which are trees. Now, in principle, okay, nobody is really interested in factor graphs which are trees. But the answers of these questions are trivial if you have trees. Now, if you have a factor graph which is a tree, then the solutions can easily written down, and actually you can just identify this message passage quantities in terms of subgraphs of the tree. So I have just explained it on the next picture. So here I'm having a factor graph which is a tree. So if you want to know what new hat is, from the message from A to I, what you are looking at, okay, you go from N to I. So you can just take the part of the graph which contains okay, the connection between A and I, and then the rest which is attached to A. So I want to exclude this side here. So I'm just having this part, and then I'm computing the marginal. Okay, yeah, I'm having a perfectly well-defined measure. I'm looking at the marginal at I, and this gives me this quantity as a function of xi. Now, similarly, if you're looking at this message passage from I to A, what I'm doing is I'm just cutting. Actually, the term message passage from I to A is used generally, but I don't find it a very good notion, because in principle you are just cutting off the connection between I and A, and look at the rest of the graph. And then again, you are computing the marginal at I, and you're getting this quantity. And you can easily check that then it satisfies these equations here. So modulo normalization here. So that's a simple exercise here. You can then also compute, if you have knowledge about these quantities, you can compute the marginal measures of the whole measure. So at I, which you just can write as a product over these messages coming from the neighboring from A to I. And evaluated at xi. Yeah. So if you have a simple way to compute these quantities, you have a simple way to compute marginal measures, and also more complicated marginal measures here. So now the interesting thing is that you can, and it's actually just an exercise to compute it, is that you can set up an iterations, and this iteration stabilizes quickly. So after the diameter of the graph, in the case you are having a tree, if the underlying graph is a tree. So you're just setting up essentially, okay, you see these are just this belief propagation equations, but I use it now as defining an iteration here. So maybe you should just okay, if you are starting with okay, you're starting say with t equal 1, and then you are just look at this expression which has appeared before, and I just use it to define that quantity here. So the new hat at step 1. And then after having this new hat at step 1, I can use again the second formula to boost that to the object at step of the iterations at t plus 1 here. So, and what it turns out is that if you are on a graph which is a tree, it stabilizes after the diameter, and then you have okay. You can also compute the marginal measure here. So in polynomial time in the diameter here. So that's of course okay, good. Now just a short thing about there's a simplification if you have just pair interactions. If you just have pair interactions. So in that case, or maybe just interactions on single variable nodes. So you see, for instance, if you have I and j and they are connected through a function nodes, so function nodes A, you are just defining, let's say, a new quantity, new bar from I to j, as you see, A is uniquely defined by I and J if I and J are connected through a function nodes and you just have pair interactions. And then you're just defining it in this way, so as from I to A as before. And then you see you can just write down one equation. In that case, if you just have pair interactions, you have one single equation. You don't have to have these two equations here. So they are just given by this equation here. So I'm taking then the boundary of I in this graph where I left out all the function nodes. Just the boundary of I are the variable nodes which are connected through a function node. This I here. So it's just this quantity. So you don't have to use these quantities here. So you can eliminate that. So and you're getting just this this equation here. So of course always understood to be modulo normalization here. So. Now the point is that of course what you're hoping, of course you are in principle not interested in factor graphs which are trees. But the hope is, and it's actually an extremely difficult point is that large factor graphs sometimes resemble, also they are not really trees. So if they are large, they are somehow resemble trees here. So, and then you hope that even in such a case, you can use these iterations and other properties from the theory of factor graphs to obtain information about these measures here. So now, so for instance, I think it was first used already by Gallagher, who first introduced these LDPC codes, which were more or less forgotten for a long time. So, but he used this belief propagation, this message passage, which he was he called them sum product algorithms. He used them for algorithms to compute approximate marginals and use them for so-called bitmap decoding here. And this topic became very popular. So after and around 2000. So it actually turns out it actually was quite a sensation, but it was already somehow in Gallagher's thesis where he introduced this LDPC code, that is LDPC codes, and particularly this decoding algorithms, but there are other algorithms also based on this belief propagation, are fast decoding algorithms which work in principle up to the Shannon capacity, so close to the Shannon capacity. It was quite, they are now heavily used, and these decoding algorithms based on belief propagation, I think, are heavily used in practice. Yeah, so. Now I come now to this Shelton-Kirkpatrick model, because that's actually the topic where I had written a paper. So you see the Shelton-Kirkpatrick model is fully connected here. Because everything, and so evidently it's not a tree. So you see every variable node is connected with every other variable nodes, and this function is just given by that. And then you are just having, as explained before, you're having a function also acting on the individual components here. So you just have situation. Now this is also not locally a tree. So you see, for this LDPC code, the nice thing is that if H is large, then the underlying graph is not a tree, but locally it looks like a tree, which is really the basic reason that this algorithm work in that case. Now this is not the case here, so it's not locally a tree, but still you have the impression that short loops in the graph are getting essentially a small weight, because these J are just you see these interactions are small. So for every pair, it's just okay. You're having this is small, so essentially this is close to 1. So for every pair, so you see every single interaction is small. So you think the interesting thing are just coming up at looking at longer distance. So because everything is interacting with every other thing. So you still have the hope that short loops are not counting, and despite the fact that it is not locally tree-like, you still hope that this with this belief propagation it could give something here. So Now, the point is, okay, in that case, the alphabet is just -1, 1, and the distribution, of course, in that special case, are just determined by the mean here. So instead of writing this new bar, which I had introduced just for pair interactions here, so I'm just computing the means of the corresponding distributions, and then I'm calling it mi to j. So okay. I'm just doing that, and then you can just write down the belief propagation equation for that here. So now there is still an approximation step. If you do the computation, which of course just a simple exercise, you're not falling on this equation here. So there's still an additional approximation step, which needs a little bit of justification, but which I leave out here. But essentially, well, what you are getting from the belief propagation are just these equations in this special case. Where, okay, I had defined these variables only for I smaller than k, and taking it independent, and then you have to make it symmetric. So yeah, just this is the equation you're getting. Now this is running under the term relaxed message passing equations here. So then you're getting these equations. Now you should okay. It's just that here. So now I want to explain that is now the main theme in principle of my talk, is what the tap equations are. So the point is, you see, you're still having equations indexed by two pairs, by a pair of the variable nodes here, this mij. You think because the interaction between the variables is in principle small, you also think that, hope that these quantities you are getting here are in principle an mi plus a small quantity here. So, and that you're just getting equations just for this mi's where you just forget about the influence of j here. So now that looks a little bit strange. But it actually turns out that this correction is small as n goes to infinity here. So now what you think is that for this mi's you just can't write down the equation where you just leave out that here. But that's not correct here. So because you're having here a large sum, and then the correction plays a role here. So now it's essentially a back of an envelope computation. You can just plug that in as an ansatz. And what you are finally getting then as an equations for the mi's are these famous Thouless-Anderson-Palmer equations, which in physical literature are considered to be the equations for the means of the measures here. So what you are getting is the first thing is what you expect, and then you are getting a correction term, which is this famous Onsager correction term here. So. But in principle, you can start with that and do a little bit of okay, it's just back of an envelope computation, and then you're getting that the correct equations for this mi should be that. So this is the Thouless-Anderson-Palmer equations. Okay, it's the only equations I know which has 3 Nobel Prize winners in the name. So namely Thouless-Anderson and Onsager. So. Okay, there is a parameter q appearing here, which is satisfies this equation, this fixed point equation. It's known that this fixed point equation, okay, it's a nonlinear fixed point equation, but it's known that if h is different from 0, then it has a unique solution here. So that's. Now, I should also talk about, and this is addressing the question also about this situation if you can more or less believe that you are in a tree or not, so in something tree-like. There's a phase transition which was proposed in the physics literature by De Almeida and Thouless, which is now called this AT condition. Now the AT condition. You see, if the AT condition is satisfied, then you are okay in physics jargon. You are in this. You should be in this so-called replica symmetric situation, which is in principle the simple situation here. So, which is a situation where you believe that the non-tree character of the underlying graph is not playing a big role here. So, And the condition is just this, is that beta square, and then you are taking that. The Q is this solution of the fixed point equation you had before, is smaller than or equal to 1. So mathematically, I have to say it's still an open problem. So many people have tried to prove that, and I think there is no serious doubt that it is correct. So that is the correct condition for this situation to be essentially tree-like in a certain sense. Is true, but mathematically it is not fully proved here. So now the tap equations, you see, it's really a complicated thing with these tap equations. If you're going into really in the mathematical physics topics here, so the tap equations are in the meantime proved to be okay. You always have to you see, for a finite n, it's not an exact equation. So obviously it should be understood in a limiting sense as n goes to infinity. And the solutions of the tap equations are known to give the correct means under actually not fully under this AT condition here, but at least for small enough beta here. So that's a mathematical proved fact here. So, but it's also known and mathematically proved that the MIs are the means of the so-called pure states. The point is that if this Thouless-Anderson, if this AT condition is not satisfied, then actually also that these equations, even in the limiting sense, have many solutions, actually exponentially many solutions. And then you still have to select certain subsets of these solutions, and this subset of solutions corresponds to the so-called means of the pure states in this. But I don't want to go into spin glass theory. So we are just looking now at the situation where this AT condition is satisfied, where beta is small, and where it's known that actually at least for small enough beta, that the MIs, the solutions of the tap equations, correspond to the mean of the measures here. So now, in principle, if you are thinking about this AT, about this tap equations, you think that you should be able to solve this tap equations by iterations here. So at least if these AT conditions are satisfied, you should set up an iterative procedure solving these tap equations, and so you would have a quick algorithms to compute the means of the spin variables under this measure for Shelton-Kirkpatrick measure. Yeah, so now this actually I wasn't aware of that was thought to be a difficult problem here. And it's actually quite subtle. So many iterative schemes which had been proposed didn't work at all. And it was actually solved in a paper of mine which appeared in 2013. And the iteration procedure is in principle what you expect here. So you're just you're looking at that at t plus 1, and then you put t, and then you put t here, you think. But that doesn't work. So actually that puzzled physicists quite a lot. So if you do it in this way, it doesn't work. You have to set up here t minus 1 here. So, and if you set up t minus 1, then everything works perfectly. But there's actually a deep reason. So it's actually it's extremely delicate, and physicists hadn't seen that. But because if you set it up in this way, you are getting a very crucial structural property which is wrong. So which if you don't do it in this way here, and the structural property is that you can characterize how these solutions behave if n goes to infinity. I have written that on the next thing here. So you know that this vector of mt as n goes to infinity is approximated in an L2 sense, which is written here just by a tangent hyperbolicus, and then you have some constants gamma s which you can compute, and then you have random variables which asymptotically are Gaussian. And they're independent for different s. Okay, they are Gaussian vectors. So you see, okay, I'm having capital N of these components here. There's a non-trivial covariance structure which you can compute here. But they are independent in s. and they are not changed with the iteration. If you're increasing from t to t plus 1, you still have here the same variables as before, but you are adding a new independent one here. So, and then what turns out, and that's true for all beta and h, the structure property is true for all beta and h. And then it turns out that actually always the sum of this gamma s square is smaller or equal to this parameter q I have written before, but it's equal to q if and only if the AT condition is satisfied. So which would then mean that if and only if the AT condition is satisfied, this part goes to 0, and this means that the iteration stabilizes here. So that's in this sense here. So. No, it actually, okay, in the paper I actually haven't proved that actually the M's really give the means. So that's still a different thing to do. So of the model. And that actually just has recently been proved by Markov Chains from Minneapolis. But actually you cannot prove it in the full AT region. So this AT business is still somewhat okay. Very puzzling and difficult business here. So now, okay, I think I have about 10 minutes to talk about the next topic, which is okay, which was historically quite interesting, namely about this compressed sensing here. So now the point is that this algorithm I have here presented for the AT. For this tap equation, which I have presented here for the Shelton Kirkpatrick model, a similar algorithm was found before. But and the people had realized that it works properly in the correct region here. But it was just realized by computer experiments. And then based on the technique I had developed in my paper, the people were able to prove that it really works. And that's in a topic on which I have never worked. So it came quite as a surprise to me. That's in what is called compressed sensing here. So one is just looking at the standard linear regression model here. So you're just looking at, okay, you're having some parameter you want to estimate. You're having this matrix here, which is supposed to be known, and the measurement YA is just obtained by this. Okay, that's the standard regression model plus an error. So I'm not talking about the errors also, because in what I'm talking about, it's not playing a role. So you're just looking at that. Now the point is that it is, you see, for standard regression, you have to have small n, so which is the numbers of equations you are having has to be bigger than capital N here. So, but of course, statisticians among you know that now. Okay, many people are much more interested in cases where the number of equations is smaller than the number of variables you have in principle. Of course, then you can do nothing. So statistically, except you know, and that is parameters betas are different from 0 only in a small number of cases here. So you're looking at a situation where you have an underdetermined system here, but where you know that these betas, just a few of these betas are different from 0. Now, what I'm again doing is I'm looking at an asymptotic theory where capital N goes to infinity, and I'm taking small n proportional to capital N. So with the parameter delta, so small n is delta times n, and I'm assuming that the numbers of m where the parameters beta are different from 0 is also proportional to n. And with a proportionality factor rho times capital N. Now, the question is, okay, just if you leave out this error thing, it's just a question about essentially about linear algebra. Can one typically identify the beta from Y? So knowing that the betas are different from 0 only in a smaller number of cases here. So is that identifiable here? And Now one has, of course, if you have a particular case, this is very difficult to decide. But if you want to do a theoretical investigation, what you are doing is you're making a model where you assume, okay, that the capital A's are random. And then in the end, this means that you are just in a typical situation where you just choose a capital A to be standard normal, for instance, and you are taking the betas being different from 0 at the randomly chosen place, which is given, okay, the number of places where you choose it is given by the small m. And then if they are different from 0, you also assume that it is standard normal here. Now, and that is a situation there is, okay, it is, I think, in the meantime, famous theorem by Donoho, namely that there is a function phi, which separates the region where you can do the identification with the situation where you cannot do the identification here. So the function phi is, okay, it's a bit complicated to write it down. You see it on the picture on the next slide here. So what the function phi is. So what you have to do is, what he proposes is that you're taking the minimal L1 norm here. So not the minimal L2 norm, the minimal L1 norm of x's which satisfy ax equals y, so a times beta here. So, and then this, okay, this probability refers to the randomly chosen a and randomly chosen beta. So this probability as n goes to infinity that you correctly identify beta goes to 1 if rho. So you remember rho was a parameter governing the number of components beta of beta which are different from 1, so different from 0. Sorry. And if the number of places where it is different from 0 is too big, then you don't see it here. So now that of course you can solve in polynomial time because you can do it by okay, linear programming here. But the algorithm for linear programming is also okay for big systems. It's obviously also computationally a bit a problem. And then that I think was coming up by engineers, by some heuristics from engineers as an alternative to have an iterative procedure here. So now what they are doing, okay, at the step t, we are just looking at y, which is okay, this observed a times beta. So and then you are looking at you are plugging, okay, you're applying a to xt. You are looking at the difference. Then you're just looking at this quantity. You are adding xt plus the transpose of t to z, and then you are having a thresholding. So you're taking a threshold here. So function here. So which is, for instance, you can take that one. So you see that looks something like that. So it goes like that here. So that's this thresholding function here. Now it comes with a parameter. Here you have to be, of course, careful. So this comes with a certain scale. So this p, which goes to 0 with iteration, and you have to determine what the optimal speed of this threshold business is here. So you have to do here. So you had, and okay, that was okay. That was proposed by engineers, and then it turned out that it runs fast, but it runs only fast. It runs correctly only in a smaller region than the one which was described by Donoho. So for instance, so it's obviously there's something wrong because it is not it's fast, but worse than this thing because you need more restrictions here. You see it on the next slide. Yes. Now, actually, around 2009, it was an original thesis by Maleki. So Donoho, Maleki, and Montanari presented the modification where you have an Onsager type correction here. Which in this iteration here. So you're just adding here something, and also in the adding you have to go one time step down. So it's extremely important because otherwise it's running bad. So it's very sensitive. So what you are doing, so the delta was the parameter I had before, which is the relation between the number of rows and columns in the original matrix, And then that's the derivative of this function here. And then you are looking at that here. So you see you're having the same type of thing here, but one level back, and you use it here for computing this reminder here. So now the derivation I'm giving, I'm having still it on the next slide here, okay, it's based on belief propagation arguments here. So then here you see the result, which was very striking here. So you see that the blue line is this line. Okay, that should be rho and delta. So this blue line is the one obtained by Donoho in this theoretical result here. That's this phi function here. So, and then this iterative soft thresholding did work only in somehow the region here. It's all based on computer experiments here, so only in a smaller region. But then with this Onsager type correction, it's working essentially in the proper region. Maybe there's differences, I don't know. So that's based on computer experiment. I took that from a paper by Donoho and Montanari here. So. Now this is okay. I'm just very quick, so I'm just I'm not giving. I cannot have time to give the computation. So it's actually a relatively longish computation here. You start with a model which is of the same time, the same type I've encountered before. So you see you're having here. Okay, it's a bit more complicated because you are running not on a finite alphabet space, but on the real space. And then you are having, okay, it's a little bit formal. So you're taking this, delta is not the delta we had before, this is the Dirac delta function. So you should satisfy this equation here. So that's this model here. And then you have a certain a priori measure. Now you're taking e to, okay, an exponential distribution. Now this is coming from the fact that you want to have something mimicking Donoho's theorem, because there you have the L1 norm. So you're having this measure, but which is exactly in the form we have encountered here on these factor graphs. And then, okay, you have a certain complicated procedure. So first, you have also to let the parameter beta finally go to infinity. You're not really interested in the full distribution, but just in the mean. And the variances, you are getting then equations for the mean and the variance. It's using approximations, and you have to use Berrier-Sinn theorems to justify it and things like that. And then you are getting equations which is in principle are of the same time as we had encountered before here. So, but of course they are more complicated than you're getting also these relaxed message passage equations. But they are not on the full distributions, but they are just on the means, and you're getting equations for the variances here. So that's what is happening. And then you are doing an approximation, a further approximation step to go to this tab-like business, and then you're falling on this type of equations. Okay, it takes a couple of 5-6 pages to do the computations, and then you're getting in this way out of this belief propagation business. You're getting this, and that was actually the way they found it. So because Montanari was in this business very much here. So now in the beginning they didn't know how to prove it. But after studying my paper on the tab equations for the Shelton Kirkpatrick, okay, that it was okay. It's now generalized to a considerable extent here, so that there are many papers were just by the Stanford groups, by Lerlache, Montanari, and just this year there was also a further generalization by Volkhausen Chen, which gave the same type of structure theorem I had in my paper on the tab equation for the Shelton Kirkpatrick model here. So, okay, that's about. I see in 1 hour I did just maybe just Kostya, do I have 1 minute just to explain what my original motivation was? So
1 minute for sure.
Yeah. My original motivation was to use these tab iterations actually to give a proof for this formula for the free energy, at least up to this De Almeida-Thouless line. And now, up to now, I haven't succeeded to do that. So, but I have the point is that the key idea was for the free energy. Okay, I will okay. I had explained here that we do it for the so-called perceptrons here, which comes from neural computation. You see, in some situations, you see, for the free energy, we want to evaluate this limiting behavior of the arithmetic mean of log of Zn, which is actually, you can prove that it doesn't matter if you are integrating outside out about the randomness here. So, but in some situation, you can take the expectation inside and you're getting the correct expression here. But for the perceptron and also for the Shelton Kirkpatrick, for h different from 0, this is not correct. So my idea was actually that it could be correct if you are conditioning essentially on the sigma field generated by the tap equations, because you are thinking that the tap equations are fixing the means. So that's the key idea, and to do something like that here. Now that worked for the Shelton Kirkpatrick model, but not, unfortunately, not up to the De Almeida-Thouless line. That's a paper in 2018. And there are some new papers. So one was by Nike-san from MIT and Yan Ding. So it's not yet published. So they could give a lower bound for the perceptron, okay, which is in principle a much more complicated model than the Shelton Kirkpatrick model. So they could give a lower bound up to the correct critical value. And actually some work in progress, which is actually going on very well. So that's with Shuta Nakajima and Nike-san from MIT and Chanshi Su from Harvard. We are, for this perceptron, we are evaluating the free energy with the help of these tap iterations here. So I think it's quite successful. For the moment, it's not really a new result because it's an extremely complicated proof by Talagras. But it's a conceptually much simpler argument in principle and a much shorter proof. Okay, it's not worked out in details, but it looks very promising here. So that was my original motivation for looking at this tap iterations here. So okay, maybe I was going 1-2 minutes over time. So sorry for that.
Thank you very much. Thanks for your very interesting talk. We have got a few minutes for questions, answers. Are there any questions, please?
Yes, I have one, Erwin. Can you hear me?
Yeah, I can hear you.
Yeah, that's okay. How do these, the results in the linear algebra setting, how do they compare with things like LASSO and so on? Do you know about that?
That's of course, yeah. That I actually am not really in this field. So I think it's used now as an alternative to LASSO type methods. But to which degree they can really apply it? So then that's I have not followed this business. My understanding was that what I cannot say is okay, because I'm not knowledgeable about that, is for what type of the statistical problems these things are really working. But my impression is that if it is working, it's faster than LASSO. So I had about okay, I was visiting Stanford about 2 years ago, and I had talks with Donoho. So Donoho was very excited about this message passage message passage algorithm. So my impression is that it is used. But I would have to talk. I have not talked with statisticians in the last 2 years about that. So.
Thanks.
Any further questions?
Hi, yeah, I have a question. So a couple times you said something about like needing structural results to solve these iterative equations. So can you just like elaborate a little bit? Like, what do you mean by structural results? What does that mean?
But yeah, okay. The structural result is just what I've written here. That the iteration you can characterize how the iterations behave by just computing. Computing. You see that you see in principle it's actually a little bit of a miracle. So because there are some. The point is that. It's really, if you look at it, it's really a bit strange because you see these iterations are producing something highly nonlinear. So because of course in the first step you are just having a linear thing. Okay, you just start with something, maybe you just start with something constant, and then you have something, of course, okay, and maybe in the first thing you don't have that, so you just have something Gaussian here. So but in the next time you're plugging it in, so you're getting something highly nonlinear. So now if you don't make this time shift to t-1, then it just becomes totally ugly, and you lose total control of what is happening. And that was the original problem why this iteration behaved so unstably here. But if you do it properly, then you are getting a certain that in each step asymptotically the nonlinear parts are cancelling essentially out. So in an asymptotic sense here. And then you are okay now, and then you are just getting that as n goes to infinity, this mt is just a tangent hyperbolicus of something Gaussian, and where you see in the more complicated situations which were investigated in the meantime by Montanari and Donoho and people like that. It's getting more complicated, but you're always having essentially an explicit expression about how this Gaussian part, which is appearing here inside, how it is behaving, and that you can use to prove properties of the. So this structural, okay, it's always also called structural equations for which characterize how this Gaussian part develops. If in the course of iterations, yes. So it's if you first see it's a kind of a miracle, this cancellation. So that's.
So you're just when you're doing these calculations, I mean, you set up some recursive iteration, and then you start to do the calculation, and things pile up, and so now you're trying to shift or add terms or something to get the cancellations. Yeah. That's the idea.
Yeah, it's actually a bit. If you do actually, I've talked with Montanari, I found it just by doing the first iteration, and then I saw, oh, if I do the shift, then it's working fine. But actually, there is a more deeper way to see it actually. So if you are coming from this belief propagation equation, and if you do it very carefully, if you do it very carefully, do the iteration for the original belief propagation equations, this message passage equations, and then you do the approximations, which I've just hinted at very carefully. You see that in principle you should do it like that. So in this way, actually Montanari had seen it. So just looking at this original message patches. Business, but then they didn't see how to prove it. So because there is still a tricky thing how to prove it. So that's no, it's actually astonishing. If you look now in more recent papers by Montanari and also by Wei-Kuo Chen, which has the newest, I guess the newest. Where Wei-Kuo Chen had the newest versions, so then it's also the equations which are satisfied by this Gaussian limiting behavior are more complicated. The situations are much more complicated than described here. So actually, already for the perceptron, which I had planned to explain at the end, so the things are already much more complicated than for Shelton Kirkpatrick.
Okay, thank you. So maybe one more question. It's getting late here.
I see.
No? Okay, Erwin, thank you very much again for agreeing to give a talk at our seminar. It was really interesting, and it's a pleasure to see you, although you're back
Okay,
to
it's a
Switzerland, but it's
pleasure.
great to to see people coming to our seminar. It's very pleasant, especially during these crazy years.
Yeah.
Okay, so thank you very much again.
Okay, thank you very much for the invitation to talk in your seminar. Okay, so bye-bye.